All right, well, welcome. In this video, we're going to be looking at lesson 12.2, and we're going to be looking at both parts in this video of 12.2a and 12.2b, all of which is dealing with this concept of conditional probability. Now, what we're going to do is we're going to start with a little bit of a review. We're going to look at this scenario where we have this table of different club memberships by grade. So let's just study this table for a minute so we can see here that we have three different club memberships. We have a drama club, a science club, and an art club. We can see the different grades. We have the sophomores, juniors, and seniors that are part of these clubs. So the way that you would read it is this 3 here represent that there's 3 sophomores that are in drama club. There's 18 juniors in science club. We can see that there's 36 total sophomores. We can see that there's 40 total juniors, and so on. We can see that there's 17 students that are in drama. We can see that there's 40 students in science. We can see there's 58 students in art. And we can see that there's a total of 115 students that we're looking at here. So that's how we would look at that table. So the total number of students is 115. So when it says, what's the probability of just randomly selecting a person and them being a junior? Well, remember, a probability is made up of a part over a whole amount. So the whole amount in this case, it's not segregating, saying that we're just looking at this part of the table. It's just referencing the entire table. So there's 115 students total. And out of those 115 students, there's a total of 40 juniors. So the number of juniors out of the total number of students is 40 out of 115. Now we always reduce if we keep it as a fraction, so we'll do that here. And so this would reduce to 8 over 23. So looking at the next one below it, what's the probability that they're an art club member? So again, this is not specifically segmenting any particular group. We're going to get to that in a second. But for right now, it's just focusing on out of all the students, what's the probability that they are part of the art club? And so again, there's 115 students total. Out of those 115 students, 58 of them are an art club. That can't reduce, and so that would be our answer as a fraction. All right, well, what if we wanted to just focus on different parts of this table? Like, look at this next example. Now, the way that it's worded, you'd almost think that it's going to be the same answer. It says, what's the probability that it's a junior given that they're an art club? Or what's the probability that they're an art club member given that they're a junior? It seems like, again, that it's asking the same question. But the fact that what we're given is a different amount or a different value there is going to change our probability. Because this is saying, in this first one, we're looking at, so when it says, what's the probability that it's junior given that they are an art club? So that means instead of looking at this entire table, we're looking at just this column. So in that column, there's a total of 58 students that are an art club. And out of those 58 students, 16 are juniors. And if we reduce that, we get 8 over 29. So with this other one, now it's switched it. So it says, what's the probability that they're an art club member given they are a junior? So now, focusing on just this row that are juniors, we know that there's 40 juniors, so our denominator changes, but the number of juniors that are in art hasn't changed. That's 16 would be in our numerator, and that reduces to 2/5. And this is where we can use probability to manipulate information, because these two statements sound very similar to each other. And where if we were to change this to a percent, this would be about a 28%. It's not exactly 28%, but it's about 28%, where this is exactly 40%. So like, again, I'm not getting in anything political here, but anytime there's an election, oftentimes politicians can be looking at data around the same information and can manipulate just how they phrase their statements, and neither of them are lying. They're just adjusting what they say to manipulate people to believe a certain way. So that's why, like, when you look at these two percentages, 28% of, given that a student is a junior, or juniors, given that they're an art club, is happening 28% of the time, where an art club members that are junior, that's a probability of 40%. So you can see how, if we were to look at, for example, climate change is a big hot topic. You can look at information around climate change, and you can manipulate to look a certain way just based on how you phrase it. So again, that's why you always want to mistrust any politicians, because they can always use the same data and look at it from different ways and not really be technically lying, but just manipulate the data to help you believe a certain way. All right. So it'd be helpful if we had a formula. So we do have a formula. Now what we're going to be looking at is some symbols. So when we see something written like this, that vertical line there represents the word given. So the way that we would read that is we would read that as probability of A given B. Now I don't want you to get hung up on the letters. I mean, it could be the probability of X and Y, it could be the probability of any random symbol. Okay, what's important is what you're given, that is what we're going to have in the denominator. So if given B, that's what's going to go in the denominator. That's going to be your total. Now remember, we are going to be given formulas we're going to give you formulas on the test. This is a formula that's going to be given to you on the test, so it's not going to have words on there. So it's important to understand that and is that intersection. Okay, so the intersection, the probability of A and B happening at the same time. That's the overlap. That's the intersection of those two events. So let's look at how we can use that formula to answer these questions. So this one, we're looking at Diego's tracks his sleep and coffee consumption. So when he had 0 cups of coffee, we can see that there was 4 days that he got 6 hours of sleep, 4 nights that he got 6 hours of sleep, 6 nights where he got 7 hours, and 12 nights where he got 8 hours when he had no coffee at all. And then when he had 1 cup of coffee, you could see how that changed the number of hours he got. And then you can see, again, that for so on. So for the rest of the table there. And so we could see our totals are in this last column. And we could see our totals in this bottom row. So that represents 22 days where he didn't have any coffee, 26 days where he had 1 cup, and 24 days where he had 2 cups. And again, this bottom right corner tells us that there were 72 days total that he did this study. All right, so let's see how we can use that table and that formula up above to be able to answer these questions. So again, this is looking at the word given, so that means that what's given is 2 cups. So we are going to focus on just this column. Okay, for this one, we're looking at just this column. So given that he had 2 cups of coffee, there were 24 nights where he only had 2 cups of coffee during the day. And out of those, we're looking at how many times did he get 8 hours of sleep. So that would be 4 over 24, which reduces to 1/6. We'll just keep these as fractions. Now this one looks, again, very similar, but this time we're given 8 hours. So that means instead we're going to look at this row where he got 8 hours of sleep. So given that he got 8 hours of sleep, so given that row, what's the probability that he had 2 cups of coffee? So the intersection where he had 2 hours of sleep and 2 cups of coffee and 8 hours of sleep happened 4 times out of 23, and that can't be reduced. If you try to reduce that on your calculator, it stays 4 over 23. So that would be your answer. So again, that's how we compare those two. So what I want you guys to do is I want you to pause the video and I want you guys to try these two on your own. So try those two and then hit play when you're ready to check your answer. All right, how did you do? You should have gotten 6 over 11 when you reduced 12 over 22, because again, for that one, you're looking at given that he had 0 cups of coffee, so we're looking at this column, and in that column the total was 22. And out of those 22, there were 12 days that he had 8 hours of sleep. Where for the second one, we're looking at the number of days that he got 8 hours of sleep. So looking at this part of the table, so there's 23 days that he got 8 hours of sleep. Out of those, again, there was 12 days where he had 0 cups of coffee. So 12 over 23 can't be reduced. All right, that's when we have a table. Let's look at Venn diagrams. We worked with Venn diagrams last week, and so let's look at how we could set up this Venn diagram. Now, I always like having a box around it, so then if we ever have any numbers that don't fit in the circle, we just put it inside the box outside of the circles. So we're going to fill in what we know. So we know a survey was conducted in which exercises people were likely to perform on their own. In the survey of 60 people, okay, so there's 60 people total, so that's important. 40 were found to enjoy walking, so I'm just going to call this walking. And 25 people like biking, so we'll call this biking. Event B. And 12 people said they enjoy both. Okay, so that both, that's very important. So we know that intersection where they both like to walk and bike would be 12 people. Now there was 40 people that enjoyed walking. So that means this circle has to total 40. So 12 of them we already have written down. So that means 28 only walk and don't bike. So 28 plus 12 would be 40, or 40 minus 12 is 28, however you want to compute that. And then this circle again, we're 12 people we already have recorded. 25 like biking, so that means 12 we already have written down, so that means there's 13 that only bike and don't like to walk. All right, let's add these three numbers together. 28 plus 12, that's 40. 40 plus 13 is 53. Well, remember there's 60 people total, so that means somewhere outside of here, write the number 7. So 7 represents those that don't like to walk or bike. All right, so we did part A, so we filled in the Venn diagram. So we want to figure out what's probability they like biking given that they like walking. All right, so what that means is that we're just going to focus on just those that like to walk. So there is a total of 40 people that said they like to walk. Out of those 40, how many of them also like biking? Well, that's the overlap. That is the 12. So if we reduce that, you get 3 over 10. Probability of A given B. Okay, so that means, remember, what goes in the denominator is your given. So the probability that they like to bike, that's focusing on this circle now. So there's 25 people that like to bike. And those that also like to walk is the 12. So that is the overlap. 12 over 25. That can't reduce. So that would stay as our answer. Now letter D, probably they don't like biking given that they don't like walking. So that one, we are going to, so probably they don't like biking given that they like walking. So again, we're going to focus on just this circle. So again, there's 40 people that like walking. Out of those, how many of them don't like biking? So that's 28. So we're not looking at the overlap in this case. We're looking at, in that circle, how many of them don't bike. So there's 28 of them that don't bike. So if we reduce that, that reduces to 7 over 10. So I want you guys, now in your guys' notes, I'm going to add that here, but you guys have in your notes letter E. Letter E is probability that, so this A prime, that's what that is, that's the way we read it. That means that the not A, so remember this is not A, or those that don't like to walk. Okay, so like this one up here, we could have written this as a probability of don't like biking given that they like to walk. We could have written it like that. So that's what they're doing here. So this one, again, letter E, we would read that as a probability that they don't like walking given that they like biking. So why don't you guys go ahead and attempt that one on your own. So pause the video and hit play when you're ready to check your answer. All right, let's see how you did. You should have gotten 13 out of 25 if you struggled with that. The reason why is, again, we're looking at what we're given. We're given that they like to bike. So that would be all of circle B. So there's 25 students or respondents that were in circle B. So out of those, how many of them don't like to walk? That would be the 13. So 13 over 25, that can't be reduced, so that would be your answer. All right. So now let's look at this next page. So this just reiterates the same formula that we had in the front. But now this is going to just look at, we're going to have some problems that are fractions. And so I just want you to see how we can simplify this using fractions. So again, we're asked in this first problem, what is the probability of B given A? And over here on the left, they give us, instead of having a Venn diagram, they actually just flat out just give us the different pieces that we need. And so we're just going to plug it into the formula. So we know probability of event A is 3/4. We know the probability of event B is 2/3. And the probability of A and B happening is 1/2. And so remember, what's given to you, that's what goes in the denominator. So the probability of event A, the 3/4 goes in the denominator. And probability of B and A doesn't have, you might be wondering, well, what about the order? A and B, B and A, the order doesn't matter. So that goes in the numerator. So what we have to do here is we have to use keep, change, flip. So we're going to keep the numerator the same, change multiplication, flip the other fraction, so that becomes 4/2. And, I'm sorry, 4/3. And now if we multiply the numerators together and the denominators together, we get 4/6, and that reduces to 2/3. So with this next one, the probability of A given B, I want you guys to try this one on your own. So again, use the information on the left, set up the fraction, and then do keep, change, flip, and then simplify, and if possible, reduce the fraction. So go ahead, try this one on your own. So pause this video and hit play when you're ready to check your answer. All right, how did you do? Did you get 3/4? If you did, good job. If you didn't get that or had a hard time with it, just remember again, what you're given always goes in the denominator. So the probability of event B goes in the denominator. So looking over here, we see that's 2/3. The intersection of A and B happening at the same time is what goes in the numerator. So that'd be 1/2 again. And so then we want to do keep, change, flip. So keep the numerator as 1/2, change it to multiplication, and then flip the denominator. So 2/3 flips to be 3/2. Multiply the numerators, multiply the denominators, you get 3/4, and that can't reduce. All right, so let's look at one more problem like this, and then we're going to talk about false positive and false negatives. All right, so this scenario, we have these 6 cards. Some of them are white cards, some of them are blue cards. And then the cards are numbered 2, 3, or 4, and so you see some of them are 2s and 3s and 4s. And so we want to find this first one. So B represents a blue card. T represents getting a card with a 3. So we want to find the probability that we select a blue card given that it has a 3 on it. So these are the ones that have 3s on them. So there are 3 cards that have a 3 on it. Out of those 3 cards, how many of them are blue and have a 3 on it? Well, we can see that that would be these 2. So there's 2 out of the 3 that are blue and 3. So that's it. That can't be reduced. That's how easy it would be. So this other one says probability that it's blue given that it doesn't have a 3. So we want to look at the cards that do not have a 3. So that would be this one, and this one. So again, there's 3 cards that don't have a 3 on it. Out of those, how many of them are blue? There's only one that's blue that's got a 3 on it. So that would be a 1 in 3 chance. Pretty simple. So again, just another scenario that we could look at. All right, so the last thing we're going to do is we're going to talk about false positive and false negatives, and then review how to create a tree diagram and see how that can work in this situation. All right, so go ahead, pause the video, and write down these definitions, and then hit play when you're ready to move on. All right, so out of these 2, so let's talk about a false positive. A false positive says that it's a test that says you get the test results, and the test says that you have the disease, but you actually don't. So what often happens is if you ever test positive, it doesn't even have to be a disease, even a sickness. Like let's say you test positive, you do a quick test and it tests positive for strep throat or for mono, or maybe something even worse like cancer. They're always going to follow it up with another test just to confirm and make sure that we didn't have a false positive. Because they want to test to make sure that you actually do have the disease. We want to make sure that we don't test that it wasn't a false positive. And so if it comes back the next one negative, well then they say that, okay, well maybe that first one is a false positive. The worst of these 2 is a false negative. A false negative is when the test says you don't have the disease, but you actually do. Because guess what? If you test negative for strep, if you test negative for any virus, test negative for cancer, whatever the case might be, they're not going to follow it up again. Because usually they just assume that that's going to be the case, that you just tested negative. But the worst case scenario is you test negative and you actually have it, but the test says you don't. Because that might mean, especially with a situation like cancer, that means that you moving forward, assuming that you don't have the disease, but you actually do, and it's growing and getting worse. So not the best case. All right, so let's look at this scenario on the left. It says when people go to the doctor's office with a sore throat and think they have strep, 30% actually have strep throat. It noted that a current test for strep throat was 80% accurate if you have strep throat and 90% accurate if you don't. All right, that can sound super confusing if we don't break it down. So that's why having a tree diagram is really going to help simplify things. So let's start out. So we have 2 possible situations to begin with. You walk into the doctor's office. When you walk into the doctor's office, one of 2 things is happening. You either have strep, well, can't spell, I guess. You either have strep or you don't have strep. Okay, those are the 2 situations. You have a sore throat, maybe it's just allergies, maybe it's just a cold, but you're going in thinking you either have strep or you don't. And they tell you that 30% of the time that people go into the doctor's office to test to see if they have strep, they actually have strep. So that means 70% of the time they don't have strep, they have something else. All right, so that's the first scenario. Now we have what's going to happen, because you're going into the doctor, they're going to test to see if you have strep. So some people are going to test positive. Some people are going to test negative. Some people that don't have strep are going to test positive, so that's a false positive. and some are going to say that they don't have strep, so test negative. So having strep and testing positive for strep, that means the test confirmed. Having strep but testing negative, that's what we talked about second there, that is a false negative because it's saying that they don't have strep but they actually do. And then going on the bottom branches there, so not having strep, testing negative for strep, well good, that means the test did what it was supposed to, but testing positive when you don't have strep, that is a false positive. So let's see how often that happens. So going back up, we can see that 80% of the time was accurate if you have strep throat. So you have strep throat, that means you test positive for it 80% of the time. That means 20% of the time you're going to get a false negative. 90% of the time is accurate if you don't have strep throat. So that means you don't have strep throat and it says you don't have strep throat. 90% of the time it's accurate for that. So that means 10% of the time it's wrong. So that means you have a false positive 10% of the time. Now, just like we've done in our previous tree diagrams, we're going to find the totals by multiplying these together. So if we take 0.3 times 0.8, we get 0.24. 0.3 times 0.2, we get 0.06. 0.7 times 0.1 gives you 0.07. And 0.7 times 0.9 gives you 0.63. So those are our totals. Again, you can just double check. Remember, these totals should always have to be 1. They do, but that's a good kind of way to check to make sure you're doing it right. So now, this is where it gets a little tricky. It says, what is the probability that a person who receives a positive result from this test does not have the disease? So we're focusing on those that have a positive result. So think of it this way. Here's one way we can look at it. If we want to do a probability, we would put the denominator would be the total. So we're looking at out of those that have a positive result, what's the probability that they did not have strep? So that means the numerator is going to be the probability that they test positive and no strep. So again, because it says that out of what is the probability that a person who receives a positive test result, we're going to have 0.24 plus 0.07 or 0.31 in my denominator. My numerator is going to be out of those, how many of them test positive but didn't have strep? And that is just the 0.07. Now, just like fractions, we never have a decimal in both the numerator and the denominator. So if I divide these, 0.07 divided by 0.31, we get 0.226. So we can say 0.226 is your probability, or 22.6% would be the probability of someone that tests positive that doesn't really have the disease. All right. So that's it for conditional probability. So with that, good luck now as you work on your assignment.